Thank you very much. Thank you for being here. Let me remind what we were doing last time. I finished on the statement of Leavitt's growth theorem for automorphisms of free groups, and I promised a sketch, an idea of proof. So here's the statement. So you take an outer automorphism group, and the elements of the free group are either of polynomial growth for this automorphism, meaning that when I iterate the automorphism of the element, I get new elements, and the cyclically reduced length of this new element is growing at most polynomially, or it has exponential growth, meaning that the same thing is growing at least exponentially. And moreover, the polynomial growth arranges nicely in subgroups, meaning that an element is of polynomial growth if and only if its conjugacy class meets one of boundedly many subgroups, depending on phi, and that are somehow simpler than F because the sum of their rank is smaller than the rank of F. So I will try to give the idea of a proof, which will remind us the object of last time. You remember that, idea for, we had several classes of automorphisms, and for those that are fully irreducible, we have a special tool, the train tracks. So I will pretend that I am in this case, so I can use the train tracks that I introduced. Actually, there are more involved train tracks that can be used in larger situations, but I'm doing the best case scenario. So for fully reducible automorphisms. So represent phi by a train track map. So what is it? It's a map F from X to X. X is a graph, always the same for me, carrying the fundamental group F. And it has this special property that there are those legal paths, and I can put a metric on this graph so that on the legal path, there is the stretch of factor lambda larger than 1. Okay, now what does it mean? It means that F is the fundamental group of X, so F is acting on the universal cover of X, and the universal cover of X is X tilde, and it's a tree. So I have the train track map that actually can be seen on the tree, but perhaps I'm not drawing it. And on this tree, I have an action of F. By deck transformation. The action like on the Cayley graph, on the Cayley tree of the free group. But now I have this automorphism, and I can precompose by the automorphism. and I get a new action on x tilde. And I can do that another time. And I get a sequence of actions on x tilde. And each time, look at an element given by a legal loop, it gets larger and larger and larger. This one I know it will grow. So I have an element, my preferred element perhaps, and in each action, it gets larger and larger translation length on x tilde. I don't like that, I want to rescale, so that I see something about the same for this kind of element. So, and I write here. So phi gives a sequence of action of x tilde, and I want to rescale by the magnitude of lambda to the n, so that those legal loops, they get always the same translation length. I know that nothing will go faster than lambda to the n. So I'm a bit fuzzy here because that's an interesting part, this rescaling, and I'm just saying, well, rescale in some way. Rescale by about lambda to the n. Okay. So that everything that grows slower than lambda to the n, I mean, the n is the index of my sequence. I have a sequence of action indexed by n, and for each of them I rescale by lambda to the n. Everything that grows slower than lambda to the n will become elliptic in the limit action, or pass to a limit. Also, this step is a bit fuzzy. I don't explain to you how to pass to a limit from a sequence of action, but you can perhaps have an idea that this sequence will start to look like some sequence on some limit object. So on some limit object, we call it an R3. And everything that grows smaller than lambda to the n has become elliptic in this R3. Fixes the point. And I have something more on this R3, I don't explain much about it, is that I can qualify the action. It will be what's called a very small action, and it comes also with an homothétie, which comes from the automorphism. And with these tools, with this vocabulary that I don't explain at all here, you can prove that no element, if an element is elliptic, it fixes only one point. Arcs in this limit tree have trivial stabilizers. So you have a picture of an action of a group on something that looks like a tree. Arcs, so something that looks like edges, have trivial stabilizers, but some points, some vertices, have some stabilizers that come from the elements of smaller growth. Well, if the world was like, it's easy and all, this would be a simplicial action. It's not, but And a simplicial action on a tree like that with trivial edge stabilizer gives a free product decomposition. And the factors are, of course, of smaller rank than the whole group. So you would get that the smaller growth is encapsulated in certain subgroups, like in the statement. Of course, it's not like that. It's an action on R3, and you have to invoke Rip's machinery. To analyze the action. Again, that's a step I don't do at all here. It's just some vocabulary point. But this theory, this very important theory, gives you elements of structures of groups acting in a nice way on R3s, and this is the case. So it gives you that the elliptic subgroups are like in the statement there. It's not yet the polynomially growing elements, but you have reduced the problem to smaller rank subgroups, and you do again. You do over on the smaller rank subgroups. So finish by induction on the rank. Okay. And I claim that somehow, when you have done these steps, each of them is a big box, you have proved the Leavitt's growth theorem. Questions about that? On the rank of the free group you're on, you started with F, and with all this machinery, you managed to encapsulate every element that grows smaller than the legal loops, strictly smaller. You encapsulate them in finitely many subgroups of smaller rank. So in each of those finitely many subgroups of a rank, you look at what is the induced automorphism there. And perhaps there is an exponent of growth again. It will be lower than lambda, but you do with a new exponent of growth. And then it gives you another family of subgroup. And this terminates because the rank is decreasing. Lambda is the Perron-Frobenius eigenvalue of your train track map. In the case of fully reducible. I'm sorry? Which step actually uses the I explained train track maps for fully reducible automorphisms and the stretch constant by Perron-Frobenius theorem, where using irreducibility. Yes? Where does the polynomial growth come from? At some point, okay. That's true. I did not mention polynomial here in this scenario. I only mentioned things that go smaller, no, not smaller, but slower than lambda to the n. And at each step, if I apply, if I find some fully reducible situation, I can use Perron-Frobenius to show that there is still exponential. But indeed, at one step, perhaps in this case, perhaps when the rank is 1, but that's not necessarily the case. At one step, I cannot use, I cannot find any fully reducible nice situation. So there, well, when the rank is 1, an automorphism of Z, we all know both of them. And it has no growth. Yeah, so I did not explain exactly how you see polynomial growth arriving, but that's at one step of the small rank, smaller rank of this process. Yeah.
Giving some specific class of subgroups, abelian groups, and products.
Okay. perhaps I don't want to go into that. The initial RIPS machinery explains free actions on arbitrary group on R trees. We are not in this case exactly. We know the group that is acting is a free group already. And what it will give is a decomposition of the action of a free group into certain components in certain types. Yeah. A tree of actions. Okay. With this done, I can start the second part of the series of lectures, which is about the geometry of the semi-direct product given by automorphism. Okay, so first about the basics, what am I talking about? So the semi-direct product F, basics. Of F and Z given by the automorphism phi is, well, is generated, okay, I should give a name to my generators of F. By x1, xr, t, and the relators of this semi-direct product are that that the action by conjugation of t is the automorphisms that you are given. So it's really the semi-direct product by saying that the generator of Z acts by this automorphism. Recall that I'm interested in this series, or I'm interested in understanding when automorphisms are conjugate in out F. So why is this relevant? That's because of the elementary proposition. Phi, phi and psi are conjugate in the automorphism group of F, if and only if there exists an isomorphism between the semi-direct product that sends F on F and T on T. Okay, so I repeat because it's only symbols. If and only if there exists an isomorphism between the two groups given by the semi-direct product that sends F on F, it induces some automorphism here, and that sends T on T. And this just a writing thing, the automorphism induced here will be the conjugating automorphism between phi and psi. So it's just rephrasing conjugation in this case. And you can also rephrase conjugation in out. I don't remember how. Okay, the same proposition actually, but they are far away now. So they are conjugate in out F if and only if there exists an isomorphism between those two semi-direct products, such that F is preserved and T is sent, well, not necessarily in T, because we are now in out, so there is an inner automorphism that makes an ambiguity. So it's sent in TF, and the element here that will be in the image will be exactly the inner automorphism, the element giving the inner automorphism that can correct the class. Okay, again, this is really an elementary statement, but it's it makes the group in the semi-direct product interesting. And we can ask ourselves, what does this semi-direct product look like? And yes.
Yeah, is there an easy way to explain what the automorphism or what F is doing?
Yeah, okay. So again, this is an automorphism of F. I'm sorry?
Is it also going to be the conjugate?
It's also going to be the conjugator from phi to psi, but it will send little phi to little psi composed with some inner automorphism, which is here. And okay, what does F semi-direct Z look like? The first insight of this comes from topology and comes from surfaces. I'm not going deep into that, but for those who are familiar with this, the first insight from this comes from when you replace F by the fundamental group of surface group of genus larger than 2. That's not the same question, but and this is well studied for a long time, because we know the outer automorphism group of the surface group are the elements of the mapping class group that we heard in the lightning talks and a lot. When it has some irreducibility property, but I will say more precisely, some atoroidal property, that the automorphism you look at on the surface correspond to a pseudo-Anosov diffeomorphism or mapping class. It's a famous result of Thurston that this group is actually hyperbolic. What is this group, by the way? This group is the fundamental group of the mapping torus of the surface by the diffeomorphism realizing the outer class. Okay, the fact that the semi-direct product is a fundamental group of the mapping torus. Do I try to draw it? I don't know. That's a mess. So you make the surface. It's a 3-manifold, right? So you make the surface times 0, 1. You glue the two ends of it. So it's a torus for the surface as a fiber. And that's Seifert-Van Kampen lemma. That says theorem that says that the fundamental group of this construction is the semi-direct product. Okay, and then Thurston gives us insight about these three manifolds, and with condition that the automorphism is pseudo-Anosov. This is a hyperbolic three-manifold, compact hyperbolic three-manifold. So the fundamental group is hyperbolic group. The semi-direct product. Okay, so that was the inspiration that is given to us by surface groups. And now, yes. So you choose, so from the group theory part, you choose an outer automorphism of the fundamental group of the surface. By Berden-Nielsen theorem, you turn it into a mapping class of the surface, meaning a class of diffeomorphisms up to isotopy, of homeomorphisms up to isotopy. And the statement is if the automorphism is atoroidal, then the mapping class is pseudo-Anosov, and then the semi-direct product is hyperbolic. So, should I say two? After this, I can go to the case of the free group with the same assumption, and that's Brinkman's theorem. And it is exactly the analog of what Thurston tells us about surface groups, but for free groups. So, theorem of Brinkman in 2000, I think. If F is free, not recall that, but and phi in put F let's take an hot. The semi-direct product is word hyperbolic if and only if the automorphism, it's our class, is atoroidal. And it gives me the opportunity to explain the easy part and explain the word atoroidal. We've seen atoroidal in the first lecture. It means that no conjugacy class, no non-trivial conjugacy class is ever preserved by any power of phi. Okay. So in this construction, that I drew here, what would it mean for the automorphism not to be atoroidal? I'm trying to draw what it means for the automorphism not to be atoroidal. So there is a conjugacy class. So homotopy class of loop. I choose it simple, but it's can be anything else, such that some power of it is preserved by phi. In this mapping torus construction, what does it mean? It means that if I push it through the torus several times, I find myself again on it, meaning that I just glued a torus in this construction. So atoroidal means no torus here. That's the reason of the name. That's also an if and only if. Yes. So, and if it is not atoroidal, if I can find this torus, you can see that sorry for the, yeah, going back here. If it is not atoroidal, so if I can find this torus, you can see that in this object of which I'm computing the fundamental group, I have a torus. So I have a subgroup. So I have a subgroup that is Z plus Z. And this cannot happen in a hyperbolic group. Or you can find this subgroup Z plus Z algebraically looking at the semi-direct product, but it's pleasant to have it topologically. So in this discussion, what I just said is that if it is word hyperbolic, yeah, of course it is atoroidal. So this is easy. How can you do the converse? And I will try to sketch it again. Very briefly, well, perhaps not briefly, but very incompletely. So you are assuming that the automorphism is atoroidal. You want to show the geometry of this, this group. And again, I will restrict myself to the case of fully irreducible automorphisms. And how to show that a group is hyperbolic? Well, we have some criteria and combination theorem that explains when constructions give hyperbolicity. And there is a very useful combination theorem that is Besvina-Fein combination theorem. Let's say a particular case of it. Say that okay, what should I say? What does the Cayley graph of F semi-direct Z look like? Well, I have a nice subgroup that I understand. It's F. So its Cayley graph looks like a tree. I know that. It's a free group. And then I have as many cosets of F as I have integers. So I have a line of tree. Each time it's the same tree. And they are arranged by on the line. And I have the generator T because so far I draw only edges for the generator x1, xn, and the generator t. What it does, well, it conjugates an element. So perhaps this is labeled by x1, and t will conjugate it to phi of x1. So if I do t phi of x1, t inverse, I find x1. I hope that's what I wrote earlier. But if it's not the case, it's just flipped. So it's not horizontal edges. They are going to give us the stretch on some paths, the red edges. Okay, because if I start to see large rectangles everywhere, I start to see pieces of a grid, and it doesn't look like hyperbolic at all, pieces of a grid. So I hope I don't see that. So I have this picture as the Cayley graph of F semi-direct Z, and the Bezzwina-Fein combination theorem tells us something about this situation of lines of hyperbolic spaces. It tells us that such a line of hyperbolic space will be hyperbolic if some conditions are satisfied. And in particular, what is called the flaring condition. And flaring says that everything interesting you will see in a tree, when you push it by the red arrows at the end of it, it will have to grow. And unfortunately, this is, when I just said it like that, it's simply not possible that it holds. So I will state it more formally, and it's less engaging than just this picture that everything has to grow when you push on the right. So I write it in the case of the situation we are in. And it says that uniformly, so for the same lambda, and uniform in time, I would say, either when I push forward, I kind of see this line as a time flow, not either if I push forward n0 time, push forward n0 time, I get definitely longer lambda times G. Or, when I push backward, I get longer. Because you see, the picture you want to have for some displacing element, so this is an element that moves in the tree of this length, and I want to push it forward. I want to see either this or that. It goes exponentially fast, grows exponentially fast in either direction. But you can see that if I chose my element to be this one, if I push only forward, it will decrease. It will decrease, it will decrease for a very long time, and I don't know when it will start to increase. So that's why you have to look at either ways. And now we want to see this picture, the flaring condition, in these lines of trees. But we know that the train track that we are given, they give us some stretch, definite stretch, in the forward direction for all legal loops, for all legal paths. So the game will be to, for all element G, arbitrary, to look for what happens at illegal turns. That's the only culprit for shrinking G when I push forward. And the illegal turns, I told you, they don't appear. They are here in the beginning, and sometimes they disappear, but they don't appear. You don't have a new illegal turn that occurs when you are using a train track. And all the game is to see that if the pattern of illegal turns keep constantly surviving for a long time so that you still have some cancellation for a long time, then it's time to look at the converse map and argue that you cannot see that on the converse map, the map for phi inverse. And that's the idea, and I'm not digging into further here. So use train tracks to find sufficiently many legal paths for phi or phi inverse. It's very sketchy, but this is really how it works. Okay. For legal loops. Sorry? No, not necessarily, not necessarily. If you, even with that toroidality, it doesn't give you a legal loop. For legal loops, you already know that pushing forward will grow exponentially fast. So the picture I draw on the left, when you see that you have necessarily elements that will shrink for arbitrarily long, tells you that those elements, they have illegal terms and so on, and they have simplification, cancellation going on for very long. So they are not legal. They are not legal. Yeah. Yes. I did not make the connection between the end of the argument and toroidality, really. So there is a part in the end of the argument that when you see that something is not going in one direction and in the other, then you have only finitely many, somehow, configurations of the kind, and using a finiteness property, you will find some repetition and an element that is a toroidal element, an element that is preserved by phi to the end. That's really just the skeleton of it. Yes.
Maybe not in detail, but if it is not fully irreducible, is it a similar idea?
Okay, so if it's not fully reducible, my preferred trick is to consider a maximal invariant three-factor system and use fully reducibility relative to this three-factor system. And you have a similar theorem of train tracks due to Francavilla and Martineau. And you work with the free product, actually. And once you've done this work on the free product, you look at what happens in the vertex groups. Talk about it later. Yeah. Okay. So what about non-atoroidal? And there is still a nice geometry, and the insight of it comes from an idea of Gotero and Lustig. Who proposed that it should be relatively, the semi-direct product should be relatively hyperbolic. So relative hyperbolicity, we heard about it a couple of times, I think. It was not, was it defined? I don't think it was really defined. I don't remember, sorry if it was defined. It's like hyperbolic groups, but you have subgroups which are completely shortcutted, coned off. So you ignore everything in their geometry, and the rest should still be hyperbolic in a strong sense. Okay. And relative to what should it be relatively hyperbolic? Relative to what happens in the polynomially growing subgroups. In the polynomially growing subgroups, you cannot see hyperbolicity because you cannot see this exponential flare requested by the Svina-Fein theorem. Okay. And I said should, but actually now, so they propose this in an unfinished work. But the work was completed, and it's now a theorem. And it's a theorem of Pritam Ghosh and myself and Lee on the other hand. That indeed, for all phi in hot F, well, the semi-direct product is, okay, give notations. Let A1, AK be the polynomially growing subgroups. And F semi-direct product Z with phi is relatively hyperbolic. With respect to subgroups of the form AI semi-direct Z. I don't write the automorphism, but that would be the generator of the normalizer the extra generator of the normalizer of AI. So perhaps it comes from a power of phi times f, times an element of f. Okay. I'm not going to sketch this because it will be a bit redundant with this part. It uses train tracks, but in free products. Well, for the way I think of the proof. It uses train tracks in a pre-times way, but other train tracks. And the combination theorem. So it's just, yeah. And it's just. It would be kind of the same sketch, but it's not the same proof. Okay. Let's go to applications. That I will use in the third lecture, that will be tomorrow. And it's about the conjugacy problem. In OUT F. So, by the proposition earlier, we know that the conjugacy problem, so the problem of knowing whether two elements are conjugate or not, having a method to know that, it's now, it can be read as having a method to know whether two semi-direct products are isomorphic with an isomorphism that preserves the factor f, and also the orientation of the semi-direct product sending T to TF. Let me call that the fiber and orientation preserving isomorphy problem the fiber and orientation preserving isomorphy problem on semi-direct products. The isomorphy problem would be knowing whether the group are isomorphic, and I add this condition that the isomorphism should preserve the fiber, meaning the factor f, and the orientation, meaning the positivity of the exponent on T. Okay, so here an earlier statement. So that's a theorem that I obtained in 2016, I think. Okay. In the case of atoroidal automorphisms, yeah. In the case of atoroidal automorphisms, the game is to compare two hyperbolic groups. And we know by Cellar and Girardel and well, a work I have with Girardel that the isomorphic problem for hyperbolic group is solvable. But yet we are not done completely because we had to add this strange condition that the isomorphism should preserve the fiber. So there is a special study here to make sure that we can detect when they are isomorphic as abstract hyperbolic group, whether we can place the fiber correctly through an isomorphism. I don't want to give more details about that, but more perhaps talk about the expected relatively hyperbolic version of this point of view. Yes. Yes, those are the groups of the growth theorem. Yeah, exactly. Yes, all the tori will be in the AI because every time you have some element that fails at toroidality, well, it grows, it does not grow. So it is of polynomial growth, so it is conjugate to one of the AI. Yeah, so every time you have a torus in your suspension, it does not grow, so it is in one of the AI. So it is in the relative hyperbolic structure of this group, of this group, which is fortunate because otherwise it could not be relatively hyperbolic if it were tori running around. Okay. Okay. So let me give what. So I'm becoming a little. Perhaps you noticed. I'm becoming a little. More sketchy and fuzzy as time passes, and because I did not give the sketch of the last statement, and I won't even give the statement of the next statement. That's a work with Nick Twican. Nicholas Twican. Yeah, so that when you try to use this strategy for relatively hyperbolic groups, after all, we know how to solve the isomorphy problem for certain relatively hyperbolic groups, so why not try this strategy? Then we obtain that the conjugacy problem for ut f reduces to problems in the suspensions, in the polynomial suspensions. And it's really not an empty statement, or it's not a statement, I guess. So it's not an empty statement because it means that you can forget everything about the exponential growth everywhere. This will be taken care by some method of relatively hyperbolic groups that will give something. And the only thing to treat is for polynomial growth automorphisms. So which are those theorems, those problems? Unfortunately, there are several of them. There are 5 of them. So first and foremost, the conjugacy problem for polynomial growth automorphism. So the fiber and orientation preserving isomorphic problem for these groups. You cannot avoid that because perhaps your automorphism is completely of polynomial growth. So I would say 1. I would say 1, like that. what I want to say, what I mean here is that automorphisms for which every element is of polynomial growth. So what does it say here, this theorem? It says that it is the group F semi-direct Z is relatively hyperbolic relative to itself. So this is an empty statement. Every group is like that. So you cannot avoid placing this first and foremost in the problem to treat. Fortunately, this is partially known. There is a theorem of Bezvina, of Fein and Handel. That gives an algorithm to solve the conjugacy problem for omnipotent automorphisms of polynomial growth. An automorphism is unipotent if its image in GLRZ, so the abelianization congruence, the image in GLRZ is trigonalized, unipotent. So that's a matrix property. Every polynomial growth automorphism has a power that is unipotent. So second, what I call the Minkowski problem. What is the Minkowski problem? It's a funny property, Minkowski property, perhaps I should say. So if you have a group G, you look at its automorphisms, and perhaps you have outer automorphisms of G that are of finite order. Those ones, you would like to see them on a finite quotient of G. What do you call that? Q finite, such that for all alpha in ut G of finite order, well, first, alpha defines an automorphisms of Q. And second, it's non-trivial. So example of famous group that has a Minkowski property, Z to the N. Z to the N, because the automorphism group is GLNZ, and Z to the N, when you map it to Z over 3 to the N, I'm mapping GLNZ on GLN Z mod 3. And that's a classical property due to Minkowski, hence the name, that this map here has torsion-free kernel. So every finite order element survives on Z mod 3 to the N. So this property, this funny property that is well known for Z to the N, we would like to see it for our very strange groups A semidirect Z. Third, okay, an orbit problem. I want to slopier and slopier as time passes. What is called the mixed weighted problem. For, well, for those groups. Okay, don't say that. So what is it, the mixed weighted problem? It's an orbit problem for the outer automorphism group of the group you consider. So if G is a group, it's the classical weighted problem would be you take two conjugacy class in G. Is there an automorphism sending one to the other? And the mixed weighted problem is that you take tuples and you ask this kind of thing. I don't want to put quantifiers there. But this is a problem in the outer automorphism group of these groups. Okay. And for, let me think. I'm missing one. Oh no, that's the same. 4 will be, yeah, okay, well, why not? The conjugacy problem inside these groups. Should have put that before the mixed weighted problem because well, it's just the conjugacy problem, you know what it is. This is more involved, it involves automorphisms. Is it known that, yes, it's known actually. That's a conjugacy problem in free bicyclic group is solvable. That's right. No, that's not the same conjugacy problem. It's conjugacy problem for the automorphisms, and here is a conjugacy problem for in that group. So this is known due to Bogopolsky, Martino, Mastakova, and Ventura. Hope I got that right. But the trick is that you also want to have it solved for subgroups. And by the way, subgroups, we know by an important theorem of Fein and Handel that finitely generated subgroups of free bicyclic groups are finitely presented. But we need the effective version of that. So effective coherence for subgroups in these groups. Okay. That's, yeah, 5 properties, that's a lot to ask. But there are hints that some of them are not, okay. I want to just finish by saying a very deep observation. I'm just kidding. All these problems are solved if the AI are just Z. The three groups of rank 1. So now we just need an induction to go further in the rank. Yeah. Yes, you give me generators of a subgroup. Well, we know it's finitely presented, and we want to compute the finite presentation. Yes, I think, yeah, you will have to. I cannot explain really now how those problems come up in the strategy of cutting the relatively hyperbolic groups and gluing it back. But that's what's happening. You have a relatively hyperbolic group. You want to know whether it's isomorphic to another one. You will have to cut in some places and compare the pieces, and then glue it back. And when you glue back things together, you have these automorphisms of the gluing locus, that is the ambiguity, leading to the orbit problem, the Whitehead problem. You know that only finite order automorphism will play into the game. So you have the Minkowski problem saying that, I will recognize those finite order automorphisms by looking at a nice quotient. So each step, there is one of these properties that comes into play. And I will stop here. And next time we'll do what can we do about out F3. And thank you.
Questions?
That's a very good question, and that's a question that tells me that I forgot to give an example of polynomially growing automorphisms. I'll do that next time. Yeah, it comes. So every time you have a polynomially growing automorphism, its growth degree is less than the rank -1. So, for instance, if you have a Z, group of rank 1, you have degree 0. So you send the generator to it or its inverse. So degree 0. If you have F2, so A and B, you can send A to A, B to BA. Well, A grows with degree 0, and BA, when you start to iterate, BAA, BAA, and it grows linearly. And when you look at a rank 3, so A, B, C, you can make examples going to A, going to BA, and C going to CB, so that it goes to CB, BA, CB, BA, BAA, and you see triangular quadratic growth. And you cannot beat that in rank 3. That will come as precious tomorrow. And in general, yes, you cannot have a degree larger than the rank -1. Okay, so we know the Minkowski property for nilpotent groups. Nicolas Nicolas is here. Yeah. And I did that some time ago when we were interested in relatively hyperbolic groups relative to nilpotent parabolics. But now it's not at all nilpotent. You see that they contain 3 subgroups in general. And well, we have also studied the case where the degree is 1 and unipotent. So this gives groups in which the Minkowski property is satisfied. Do I miss an example? 3 groups, yeah, 3 groups. The Minkowski property for 3 groups is solvable. Yeah. Or the mixed weighted problem. Minkowski. You need the group to have finite quotient. There was a no, it's okay.